Good morning, everybody. Welcome to the next day in our series. Lewis has asked me to kick off. He will be arriving shortly. My name is Quillon Harpham. I work for HR Wallingford, the second logo from the bottom down there, as a principal scientist. I specialise in hydroinformatics. HR Wallingford is a research and consultancy company for anything to do with large bodies of water. So oceans, rivers, coasts. We do civil engineering consultancy and research in that domain. The first presentation today is called the DRIHM Model Map. And the purpose of the presentation is to try and bring together everything that you have been told so far and apply it to some sort of context. You've been told a lot about meteorological models. I've been discussing hydrological models. We've done model catalogues, standards, interfaces. And the purpose of this presentation is to take all these discussion threads and try and bring them all together into something which makes the whole picture a little clearer and apply it to some sort of structure which you'll be able to see which can be applied to models. Now, most people who have been exposed to anything on DRIHM have seen this slide many times. This is the DRIHM model suite and how it all hangs together. And I have been thinking about an analogy to try and explore what DRIHM actually means to the modeling world. What we're trying to do is put DRIHM into some sort of a wider context and build an analogy for that. And several hundred years ago, I think it was an Italian, decided to try and bring a whole load of musical instruments together to become an orchestra. And I want you to imagine one or two of the conversations that took place with the musicians that he wanted to bring in as part of his orchestra. Imagine if he approached the flute player, the flautist, and said, I've got this new idea for an orchestra. I want you to play in this orchestra. What we're all going to do is we're going to get all the musicians together. We're all going to play together. And as a result, the sound that we produce is going to be bigger. It's going to be better. It's going to be more magnificent. You can imagine the flute player saying, well, I'm quite happy playing my flute around the campfire in the evening with my friends, the other flute players. We improvise. We have a lot of fun. We have no structure to what we do. It's all free, and we make beautiful music. And you can imagine the man with the orchestra saying, that's fine. You can carry on playing your flute with your friends in the orchestra, but there is also a grander vision that we want to promote. We want to play the flutes with all the other instruments that we have as well. And the flute player says, well, that's all very well, but I'm quite happy doing what I'm doing. If I play with all the other musical instruments, then I'm going to have to make compromises for what I do. I'm going to have to obey the conductor. I can't just play when I want to. I will have music written down for me. I'll have to keep quiet while the other musicians are practicing. There'll be a tuning note, so I can't just freely play. It's going to restrict me. And you can imagine the guy saying, yes, it is. It is going to restrict you. But what we will do is we will put you in a section in this orchestra with other flutes and other similar instruments to the flute, called the woodwind section, and within certain bounds you can use all the creativity you want to and all the expression you want to as a flute player, but when we get together and play the bigger picture, yes, you will have to obey the conductor, yes, you will have to keep quiet while the other musical instruments are playing. And you can immediately see where I'm going with this. For flute player, read hydraulic modeler. We do hydraulic modelling at HR Wallingford, and there is somebody coming to me and say, there's this grander vision for modelling, and we want hydraulic modelling to become part of the grander vision, because the grander vision is all about answering bigger questions, getting a more accurate answer, answering the big climate and environment questions that we want to answer today, which you can't do just with any one part of modelling. And my reply to him is, well, that's all very well, but hydraulic modelling, that's tough. That's really difficult. You know, at HR Wallingford, we are really, really clever people, and you don't understand how tough hydraulic modelling is. There's a lot to it. And I don't think if I apply hydraulic modelling in a larger context, I'm going to have to make compromises to what I do. I can't play all the games that I play with my hydraulic models by myself. And I can hear the orchestra, the environmental modelling orchestra man say, well, yes, that's all very well, but if we do need to answer these bigger questions, and I want hydraulic modelling to be part of it, and yes, you will have to make compromises. You won't be able to do all the things that you do on your own. What we must do is give you as much creative freedom as we can to be a hydraulic modeller, but when we're modelling the bigger picture together, we're going to have to make certain rules and standards which you must follow for hydraulic modelling to be appropriate. Okay? So this is DRIHM. DRIHM is one answer to this question with this use case. The DRIHM use case is flash flooding. And at the top you have a meteorological model with some downscaling, maybe some observation data sets. That's DRIHM, what we call Experiment Suite 1, rainfall. And what we're asking the meteorological modelers to do in the larger context is give us rainfall. So to me, a hydraulic modeler, I really have no knowledge of what goes on in meteorological modeling. I just need a simple interface to look at, something that I can understand. Experiment Suite 2 is discharge, and we've been discussing drainage models. And again, I might have a slightly more appreciative stance on drainage models. I might understand them a little better than I do meteorological models, but I'm not great on them. And really, all I want from the drainage model is a hydrograph coming in there, a flow time boundary condition to drive my hydraulic model. Experiment Suite 3 is water level, flow and impact, and as a hydraulic modeler, this is where I come into my own. I have a boundary condition supplied to me here, which was supplied by a boundary condition up here and some driving data. And what happens in my world down here is that we have an open channel flow model, and the hydraulic model models the water in the channel. The channel overtops, spreads some water on a floodplain. That causes damage to people, infrastructure, animal habitats, etc. So this is the big DRIHM picture, the big DRIHM use case. We can add pluvial flooding in there from runoff and groundwater flooding as well, which in some ways, due to the DRIHM approach, are corollaries. But the main DRIHM use case which we have been exploring is meteorology through drainage into an open channel, flooding, causing damage. Is that clear? Everybody happy with where we are so far with the bigger picture? So this is how the model suite fits together. And again, I'm assuming that pretty much everything I'm going to tell you won't be new to you if you've been listening to the presentations on the previous days. You'll have probably seen diagrams similar to this where each model is a yellow box. There's wharf NMM or ribs here, and around it you have other structures that we've put in place so that we can play in the larger environmental modelling orchestra. So the grey boxes here are the bridges, and what happens is that every modelling component that you see is surrounded by one or two bridges or adapters. And the purpose of those bridges is to translate from the non-standard output that each model will produce. If you come along with a model, you will be very, very lucky indeed if you're producing the exact output that I need for my model. That will be close to a miracle. So something has to happen between the output of your model and the output of my model if they have been designed separately. Yeah, what is happening in a lot of model coupling infrastructures these days is that models are being hardwired together and designed for the output of one model to be put into the input of the next. We are not assuming that here. We want to provide a more interoperable infrastructure so that the models can work together and we can add new models in more easily. So every model is surrounded by two bridges, and the bigger picture has a set of interfaces. And I'm sure this isn't news to you. We call them the P interface, the Q interface, and in the world of OpenMI, which we'll explore a little bit this afternoon, we have the O interfaces. So the P interface is precipitation, the Q interface is flow, and the O interfaces down here are OpenMI interfaces. So that is how we structure things. The meteorological models go up here above the P interface. The hydrological drainage models go in here between the P and Q interfaces, and the hydraulic model suite down here below the Q interface. So it all fits together in that structure. And before and after potentially every model, there is an adapter or a bridge to translate out of the standard file formats that we have used to structure the whole system. So I'm expecting you, if you are a modeler, to have a couple of questions for me at this stage. Firstly, you will be asking, and indeed you'll probably be able to answer part of this, what has been done to these models so that they can run on this infrastructure? And secondly, what do I need to do to my model to get it on the DRIHM infrastructure? You have a model, you want to start using it, maybe you want to expand the use case from flash flooding into other things. We have other models that we want to add in to DRIHM. What do we do? And the answer is the DRIHM Model Map, MAP. The DRIHM Model Map is essentially a checklist of all the things which you need to do to a model to make it DRIHM compatible or DRIHMified, if you like. And it's an acronym that we built up just so that people can remember all the things that need to be done to the models. So, first thing is metadata, documentation and license. The M stands for metadata, and unpopular though it is, we're going to have to provide some documentation for our licenses, for our models. Christian showed me a cartoon yesterday about software engineering where this beautiful product was developed for the client and the documentation was missing because everybody hates writing documentation, unfortunately, but we've got to provide something. So we've outlined a minimum set of metadata, documentation and license which needs to be provided with a model. If you want somebody else to use your model, you're going to have to show them something about it. Secondly, the A stands for adapters, and adapters to common interfaces for input and output using controlled vocabularies. So you've seen we have the P and the Q interface, we have standard file formats we're expecting, we have OpenMI, which is a memory-based standard for exchanging data, which we'll talk about later. We need to adapt the local model outputs to something more generic to allow them to be used. And lastly, P is portability of model components. A model component must be considered portable in order for it to be used on DRIHM, and we'll go into that a little bit later as well. So firstly, metadata, documentation and license. The metadata that you need to provide is a file of metadata which we can give to you in a Word document form. So you can even fill it in Word if you want to, containing the following details. Firstly, standard stuff, title, abstract and some keywords describing it. Fairly straightforward. A responsible person and their contact details. A rectangular geographic bounding box. What we are doing as far as the metadata is concerned is describing every model's geospatial properties with a rectangular bounding box. Now I know that some models will produce output at a point, or some model instances will produce output along a mesh which maybe describes a sea or an ocean or part of an ocean. But as far as the metadata is concerned, what we want to do is describe it with a simple rectangular bounding box in WGS 84 coordinates. So what we are trying to do is keep as much of the GIS logic out of the DRIHM portal and the DRIHM catalog, which I'll show you later, so that the validation there can be simple, even though there might be more complex things going on locally with each person's model. So a rectangular geographic bounding box around the model area that it covers. Some technical details: what languages it's written in, how many processors it usually uses, and what operating system it is valid for, whether it's compliant to standards such as OpenMI, rough runtime, that sort of technical details. URLs to code executables and more detailed documentation, and inputs and outputs. These are probably some of the most important aspects of the metadata. You need to describe the principal inputs and outputs of your model, here giving these details. And we're not talking about every single argument that goes into the model. We're talking about the base data sets it uses to function, the driving data and the base data sets that it needs to receive from other places. So we need to know the parameter, we need to know the temporal details, a temporal bounding box, so we know when the model starts, when the model finishes, assuming it's some kind of time stepping going on. The other spatial details, you can put more bounding boxes in there, type and feature type. And by feature type, I mean the geotemporal structure that the model produces results in. That is, does it produce model results as a grid series of results, a point or a point series, a mesh series, a swath? There are lots of geotemporal feature types which can be used to describe them. So we need to know that. Okay? This is the DRIHM catalog. We'll have a look at this later. It's an instance of the GeoNetwork open source cataloging tool for the standard ISO 19139 for describing spatial data sets. What we've done is we've extended it to describe models and model data sets based on the observation that essentially model and model results are a geospatial data set. Ilya talked yesterday about model catalogs, and we are currently undergoing an experiment to map the elements of the metadata we've used in this catalog to those used in other contexts around the world. So, documentation. We're going to have to ask you to write some documents about your model. General description, how to install it, how to use it, and I'm sure there'll be a full and comprehensive manual somewhere for everybody's model, so we need a link to that. And the technical changes that have been made to make it compatible with DRIHM, which we'll go into shortly. And we need a license to use it. We at least need a license to use it. We would prefer if it was open source, so use the LGPL or the new BSD open source license so that other people can get the benefits and modify the code, but we at least need a license to use it, and to use it for free. Adapters and control vocabularies. We've talked, particularly in the meteorological context so far these last few days, about controlled vocabularies. And the meteorological world, as far as I can see, is ahead of the hydrological and the hydraulic world in establishing controlled vocabularies. This is one of the key parameters that we describe. This is the main parameter we're looking for in the P interface. We're looking for meteorological models to give us output in this parameter here, liquid water equivalent, thickness of precipitation amount. To my surprise, rainfall, as far as a meteorologist is concerned, is measured in meters. But I guess there's a reason for that. I'm not going to ask about those details. So there is the definition of LWE, thickness of precipitation amount, and for many years now meteorologists have used this controlled vocabulary for talking amongst themselves for describing the parameters of meteorological models. Now, given that I have an interest in this, but it is not my everyday job. I do not need to know all of the details about all of the control vocabularies. I've seen the climate and forecasting control vocabulary, and it's vast. And I haven't got time to do a PhD in climate and forecasting control vocabularies. So what I need is a set of vocabularies. I think Bert went into this yesterday, a set of parameters which I can understand, which act as the interface from meteorology to me, if I'm somebody else. So these are the parameters that were identified by our meteorologists as the ones which we use and can be made available in the P interface for other models following. Certainly, LWE, thickness of precipitation amount, is the one the other models have been configured to use. But all of these other parameters we ask are made available from the meteorological models so that other models can be chained in when they become compatible with DRIHM. So we ask that you use control vocabularies. When it comes to hydrologic and hydraulic modelling, there is considerably less in the way of control vocabularies. If you look at, for example, the SWAN model for modelling waves, there is loads of different ways for calculating significant wave height. And they are defined within SWAN, but they are not a universal control vocabulary for oceanography. So we're a little behind in other areas. We're taking the lead from the meteorologists in defining other parameters. For example, one we call river discharge, which is the main parameter we're looking for in the Q interface. Without controlled vocabularies to describe these interfaces, it is very likely that we will make scientific mistakes in interpreting the results. We might have jumped over all the technical hurdles, but in interpreting the parameters, controlled vocabularies are absolutely vital. So we use controlled vocabularies in these file formats. So you'll know by now that we use WaterML2 for point series data using these standard parameter names, and NetCDF with a climate and forecasting version 1.6 vocabulary for the meteorological outputs. So back to our use case here, where we have Experiment Suite 1 rainfall linking to Experiment Suite 2 and Experiment Suite 3. I'm going to just take a subset of that and describe it as follows. So to summarize where we are, we have the meteorological models going through the P or precipitation interface producing grid series results. So the feature type for a meteorological model is very often a three-dimensional rectangular grid series. So that is a fixed grid with different values in different time intervals. The hydrological drainage model takes this output from the P interface, puts it into the Q interface, and the Q interface works on point series where we use WaterML2. So the feature type here is a point series, so one or more points fixed in two-dimensional geographical space producing results in going forwards in time. And then we take the open channel flow model and we do hydraulic modeling with that, with the output from the Q interface. That's how it all hangs together. Moving on to the OpenMI world, which we will discuss this afternoon, OpenMI gives us an opportunity to have two-way interfaces between models. Bert will talk about this in detail later, but essentially what we want to do is we want the models to influence each other as they run. We have use cases, for example, where water is pouring down a channel and hitting structures, and the presence of the water affects the structure, and the presence of the structure affects the water. And as structures collapse underneath the torrent of water, then the modeling domain for the water changes, and so we need a model to reflect structures and a model to reflect water putting pressure on structures, and the two interact. So we need a two-way interface between those two models. And OpenMI is a standard which allows us to do that. So as the models step forward in time, they exchange data two ways with each other as they go. And I wanted to give you a flavor at this point into how that has been implemented using OpenMI. OpenMI was released, OpenMI version 2 in 2010, and H.R. Wallingford has produced the Fluid Earth implementation of OpenMI for Windows. And we'll have a look at that later, but what we have is a couple of OpenMI components here. So, I don't know, let's say that's a flow model, and that's a wave model. And we want the flow in our lake or ocean to affect the waves, and we want the waves to affect the flow. So we want a two-way interaction between those two different parameters. Now, very often a model to somebody running it, if they're not the person that wrote it, is a black box. We don't know what's inside, we just put something in the top and something else comes out the bottom, and we don't really know what's going on inside. In order to use OpenMI, however, what we need to do is start to understand the code a little bit. And we need to isolate three aspects of the code and make it possible for an external device to run bits of that code. So what we have is a graphical user interface here called Pipistrel, which will run the OpenMI composition. And what we've done so far, as you can see on the slide, is we've loaded two model instances. That is, we've set up two models to run on a particular use case, on a particular place and time, and we've set them up to run. And because we're using OpenMI, we've isolated three aspects of the code so that Pipistrel can control the models. So usually you'd put a model in a startup file, you'd hit enter, the model would run and produce results. In the OpenMI world, we're not allowed to do that because we want the models to interact as they go. Therefore, we are initializing our model, setting up all the objects, instantiating everything, opening the files we're using. Then we perform time steps. Then we wrap up, do the garbage collection, close all the files, etc., etc. So you'll be familiar with, presumably, with this way of writing a model. You initialize everything, you have a time-stepping loop, and you have a wrap-up at the end. And what we are asking when we make models OpenMI compliant is for those three to be isolated through external functions so that Pipistrel or any other OpenMI graphical user interface can run those three for the models. Also, when we create an OpenMI component, we have a couple of files that accompany it. So there's a .xml file, .omi file. They tell you certain aspects of the OpenMI components that have been created, which we'll look at a little later. And there's some configuration files with, I don't know if this is a wave model, there'll be a bathymetry, there'll be boundary conditions for that model. So each model is set up in the OpenMI world to run independently. You can use Pipistrel just to run your model. It will run it all the way through, finish, results. Or you can combine your model with another model, do the model interactions, and produce the results together. And this is what happens. If you are eagle-eyed, you will have noticed that those outputs do not fit into those inputs. So we need an adapter. Now again, in the modeling world, you're very lucky if the outputs you produce will exactly go into the inputs of somebody else's model. There'll be temporal interpolation, there'll be spatial interpolation, there'll be unit transformation, at least, to do between the two models. And in the same way as we provide bridges or adapters between models in the chain that we looked at in DRIHM, here we have an adapter that works in memory as these models run to adapt any necessary changes that take place between the two models. One of the models will be assigned to be the trigger, and this implementation of OpenMI works by pulling data. So model engine 1 here, let's say this is the flow model, will drive the composition, and it will ask for data from the model engine 2. So Pipistrel begins and runs the initialization function of both of the models. They're both live now, ready to go. Then it starts running time steps for model engine 1. Model Engine 1 now needs something from Model 2. Model 2 runs time steps until it can provide it. Maybe Model 2 then needs some data, and Model 1 will run until it can provide it, and so it goes on in that fashion until the model's complete. Now, I'm not pretending that, I mean, there is only so much programming you can do using PowerPoint. So this is not exactly what happens. You can get deadlock situations where the models are asking data from each other at the same time, and Pipistrel has been coded to avoid deadlock situations like that. But I'm hoping that this gives you a flavor of what is going on as the composition steps through its time steps. So the models are waiting for one another, swapping data between each other until they are ready to complete. And then, as the models complete, Pipistrel will run the complete functions within the models, and both models will produce their results. So the models will have influenced one another as the composition runs. Is that clear? Yeah, okay. Portability of model components. We ask that model components are made portable. Firstly, what we mean by this is this, that the component requires only standard installations of its supporting system software. Now, I don't want someone to come to me and say, I've written a model in C#. It essentially uses .NET, but I've made a lot of tweaks to .NET, and I've got this sort of special installation of .NET which runs. We want standard installations of all of the supporting software, operating system, all of the software stack, standard stuff. Any special tweaks you want to do it within your model. Secondly, that the model component provides all binaries and libraries on which it depends, apart from standard stuff. So if someone has written a model in Python, Python is usually bundled with a whole load of stuff for standard and a whole load of other libraries that are added on. We don't want the person saying to us, hey, I've written this model in Python, and oh no, I left all of the special libraries that I've used or created for my model somewhere else. Please bundle everything in it that isn't very heavily standard. And thirdly, the component makes no assumptions about absolute directory structure. Within the component, of course, there will be a directory structure of inputs and outputs and arguments and all that. That's fine, but make that relative. You'll be amazed how often if you run a model on your machine, try and install it on another machine and run it, it doesn't run because there's an absolute path hidden in there somewhere. So a good test is to take it off your machine, install it on a completely clean machine and check that it runs. Very often it won't. So we make no assumptions about absolute directory structure. So we've done all that. We've done a DRIHM model map and we are ready to implement our model within DRIHM. From a workflow point of view, how does that look? Well, essentially, every model that I've ever seen is some sort of executable or DLL or something, some sort of engine that will run, and it is accompanied by a bunch of configuration files to apply it to a particular time and space. It's an environmental model. In a DRIHM world, what we are asking is that there are standard interfaces, and coming from outside might be WaterML, might be NetCDF, it might be something bespoke, and going to the outside, that might be required as well. So what we've asked is that there are these transforms or adapters or bridges that take you to and from the common standards. From a workflow point of view, however, this is very straightforward. From within an individual component, we are asking that you run that, then you run that, then you run that. 1, 2, 3 steps in a workflow. So I want you to consider a component which runs in DRIHM to being that whole thing. Essentially, it's one big component, but it takes standards in and produces standards out. And from my point of view, I don't really want to care what you've done inside. I probably do. I maybe need to know some of the assumptions that you've made. modeling is a minefield, but really I don't want to have to fully understand everything you've done in your model. I just want to understand the interface between my model and yours, have a conversation with you about assumptions and some of the other details. So that is a component, that whole thing. And how it fits together in DRIHM, if you remember we had meteorology, hydrology and hydraulics, is as follows. This is a typical DRIHM workflow at a macro level, where every purple box is one of those components that I described on the previous slide. So we start off with a meteorological model component. We might have some sort of optional visualization. Maybe there's some stochastic downscaling as well. But essentially what we are doing is we are passing the driving data, and in the DRIHM flash flooding use case, what could be considered the water. We just want to know how much water there is at each stage. We'll pass down to the next stage. Again, we are passing driving data, the water, from there into another set of models following. So here's the drainage model, here's the hydraulic modeling composition. At each stage, we simply want to know how much water is coming to us at the next step in the workflow. Now, what we can do at this stage, if we want to, is produce an ensemble of many copies of this and run that as part of the workflow, and then collect the results together at the end. Just for the record, in the DRIHM case, that's a little OpenMI composition within there, but you can consider the whole OpenMI composition as one component, which takes in WaterML2 and produces something that you can display on GIS. Thank you. Any questions? Should we take questions now, or do you want to carry on?
Now, probably. I can.
Yeah. Okay. Any questions?
What about is there a drainage model? Because you had it on the last slide.
The drainage model is the hydrologic model, yes.
Oh, okay, I thought.
Yeah. That's all there. Yeah, that's the standard DRIHM use case. So we have meteorology, drainage, and hydraulics. You must forgive me interchanging my terminology.
No, I just think a lot about urban drainage,
Yeah.
in the city. That's why I asked.
Oh, okay. So urban drainage would usually be hydraulic model composition of sewers. Yeah. Assembled on equation solvers. Yeah.
As Deltaris is one of the partners for this DRIHM project,
Yeah.
I'm just wondering, because some of the feature is very similar to Fuse platform, like kind of still pre-processing, post-processing.
Correct.
So I'm just wondering that how much is actually Fuse code contributed to the DRIHM project?
Bert will tell you that a lot of the logic and lessons that were learned in the construction of Fuse have been applied here as well. Yeah. So lessons learned, but no code taken.
These adapters that you have to build yourself, can you provide examples of different ones so that we can make these for our models?
Correct. Everything that we've done on DRIHM has an open source, I think it's LGPL license, so you can unpick all of the adapters and produce it fine.
Okay, thanks, Quillon. And we are going ahead in understanding the behavior of models within the DRIHM infrastructure. So now we understood that mapping the model, so applying all those steps is relevant for including a model in our infrastructure, but we have to look a little bit under the hood to understand why we made some decision and how we implemented bridges and so on for getting things working. Again, the workflow that we are looking at is composed by several nodes. Each node may include one of the applications that we are considering so far. But in reality, how the portal is going to submit the job, and in case of a job submitted to a remote resource, I'm going to wait for seconds, minutes, hours, days, how much space I'm going to consume, do I need a really powerful machine or not, and when I'm able to combine different model instances in a single chain. We analyzed each model included in the DRIHM suite, trying to understand which are the requirements and which are the constraints, and so an architecture that match the available elements in the infrastructure and the requirements to get the whole workflow working. Once we submit a job here, we get the job sent to a scheduler. This is going to select the best resource for the application that going to run. Means select one one kind of resource, like for example, we discussed yesterday AGI resources for certain kind of jobs, parallel cluster for others, and so on. Moreover, each job needs to fetch some data representing the model configuration and the model input. So we have to contact some repository, fetch the data, and wait for those data availability before starting the actual computation. And again, we have to provide some feedback on the computation and final results to the user. Each job we submit, again, has constraints. Let's start analyzing briefly the models that we are using and how those are deployed. We told yesterday that on such cluster we are going to submit a large parallel job, and on AGI resources the sequential application. More in general, this is a picture of the resources that we are exploiting for DRIHM. So beside those grid resources, we have a machine devoted to Meteo application preprocessing. So WPS is executed here because here we have all the global circulation model output data, so that are required for the WPS execution. Moreover, we are working on extending the infrastructure connecting to PRACE resources to high performance cluster that are outside the grid, so can be used even without the certificate. You know, the certificate job is a little bit tricky, so if we are able to connect to really powerful machine like this one, even without certificate, we can a little bit simplify the usage of the whole architecture. So let's go back to the requirement of those applications. In case of WRF, this is for sure, in general, Meteo applications are the most demanding that we are considering so far. We decided to submit on a powerful cluster. Up to now, we limited the execution to 24 cores in order to get shorter queues. The more core you ask for, the longer is the wait time to get all the cores available. Just to give you an idea, a medium resolution, so 500 kilometers square with a simulation like 2 kilometers resolution can require up to 5 hours on 24 cores of that cluster. if we want to have something larger, the computational time will increase tremendously. And also, in case of this rather simple simulation, we are going to produce 2 GB of output, and WRF in advanced research is not going to produce a netcdf CF file that is compliant with the architecture. So we have somehow to face the space wasted, because with many users, obviously, we cannot keep everything, and also the obvious problem of compliance with standards. In case of computation of WRF advanced research plus the bridge, we have a somehow mixed execution. Some part execution, that is the WRF code, and a sequential post-processing that is shrinking down the output, removing some of the 3D information and keeping the most relevant fields that you already saw. In this case, we are reducing by a factor of 15 the size of output data, and we get data perfectly encoded in our desired file format. Moreover, this amount of data is easier to move, to store, to send to other computational resources for continuing the chain execution. In case of a bit more interesting at a double resolution, the computational time will become about 200 hours, so 8 days for a single, again 24 hours. So exactly, on 24 cores, essentially, we are 8 times lower than real time. And output file can be about 35, 36 gigabyte. Okay. Not easy to manage, and also resource owner are going to close our accounts immediately. So again, with the bridge, we can keep the amount of data to a reasonable size, and so those considerations are available for are fine for WRF advanced research, but also for the other logical model. Essentially, the computational times and size of output are in the same order of magnitude. The second kind of application we are considering, so the stochastic downsampling, is way easier to set up. It requires just 3 parameters: the number of ensemble output that we want, the and 2 factor. One is for spatial resolution, and the other is for time resolution. Okay, just 3 teeny number, but be careful. A factor of 10 in the resolution may obviously require 100 times the 100 times the information in the output file, so the size will increase accordingly. And on the other side, also the reliability of the data probably is a bit compromised. Another information that is relevant in running RainFarm, it's working with a dimensional FFT, so it works way better on grid size that are a power of 2. So of grids that are not of this size, we sometimes increase a little bit the domain to get better performances and lower execution times. Let's move to the Hydro models. In this case, we have to clearly consider that beside the model engine, so the executable files, we need a configuration. So we need to instantiate such model engine on a particular basin. So we have RIBs for Bisagno catchment, RIBs for Muga catchment, and so on, and the same for the other models. Without focusing on a particular basin, essentially, we need to provide too much information to the model engine, and so the configuration is tricky through the portal. So we are considering already available model instances. Tomorrow we will see how to create model instances. So model experts are able to configure the model, load the configuration on the portal, so all the other users can rely on pre-configured model instances. In case of hydrological models, those are sequential application. Execution time usually is in the order of a few minutes. It obviously depends on the NestCDF that we are giving them as input. In case of a really large NestCDF with a really high resolution, obviously execution time can increase. One thing to note is that the output here is just a small XML file, so the output for a chart here is really small. Besides consideration on computational time and space required, we have also to consider that the portal has to take into account spatial and temporal coherence of the model involved in a chain. Already Quillon introduced the problem. In general, we should check for compliance. So if we are chaining a meteorological model and an hydrological model, we should take care of checking that the meteorological model is in the same area of the catchment basin that we are going to consider for the hydrological model and so on. And the same apply for the time range. If we are performing a simulation on the first 2 days of September, then even the hydrological simulation should fit in the same time frame, obviously. This is, for example, a representation of the basin required by an hydrological model executed on the Bisagno River. In this case, the meteorological model domain has to contain the basin. If we try to design a meteorological model domain that is outside or crossing the basin, the portal essentially will refuse to consider such a domain and will keep asking for a valid domain, so a domain that is fully containing the bounding box of the basin. Okay, up to now we considered workflows configured through the portal, and the portal is asking us the time frame only once, and is using in a consistent way the same time frame and the same time range for all the models. Again, is checking for right nesting of meteo domain and hydrological domains and so on. So essentially the portal is going to produce configurations that are feasible by design. In case of models that are uploaded through the name list and so on, we have to check the compatibility. One issue here is that just getting the name list, we are not aware of all the information or some information are difficult to retrieve. For this reason, we need metadata. With metadata, we can perform all the consistency check before the actual execution of the simulation. So, starting from the metadata associated to the netcdf CF file produced by meteorological model, we can check that the required domain for the hydrological model is within the range of data that we are going to produce. So essentially, if we go completely through custom portlets through the portal, okay, we are sure that the configuration is sound. If we customize it a little bit, if we load name list from files, or if we use models that are not able to be configured through the portal, then we need to add some compatibility check. Okay, I don't know if there is a question. Okay, perfect.